There are 7 days or 1 week left in the Maths Countdown series. Make sure you stick around to see what I'm counting down until. I've been counting down from 100 days, so I've covered a significant amount of maths, and if you want to see my other videos, I'll link the playlist to this video. Okay, so for today's video, we're going to be evaluating the limit as x and y approach 0 and 0 of this function. Okay, so when we are evaluating limits of bivariate functions, we need to see first if this limit exists, or at least get an idea of if this limit exists. And if it does exist, we need to get an idea of what this limit equals. So in order to do this, we're going to check this limit along multiple paths. So for this particular limit, I've chosen the x-axis, the y-axis, and the x is equal to y to the power of 2 over 3 lines. Now you can choose to check it along whatever lines you see fit, or whatever lines you think will be the easiest to check it along, and the goal is to try and prove that all of these limits equal the same number. And if you do prove that, then you have not yet proven that the limit equals that, you just know that it may exist, and you know what to work towards. And obviously, if you get limits that do not match up, then you know for a fact that the limit does not exist. Okay, and checking along multiple paths is very similar to checking from the left and checking from the right for limits of univariate functions. So for bivariate functions, our functions are existing in 3D space. And if they're existing in 3D space, we have to be able to approach this limit from every single possible angle and still get the same answer for it to exist. And obviously it's not possible for you to check this infinite number of ways to approach a certain point. Whereas, for example, with univariate limits, it's possible because you're just checking from the left and the right. But for bivariate functions, it's not so easy to check. So that's why we just do a few checks so that we can get an idea of whether it exists or not, and if it does exist, what it equals to, and then we can go ahead and try and prove the limit. So let's go and check along the 3 curves that I've told you about. So if we check this limit along the x-axis, what we are doing is we are checking it along the y is equal to 0 line. And if we were to make y is equal to 0 in this function over here, then this term goes to 0 and that term goes to 0, and we're simply left with x times by the natural log of 1 over the square root of the absolute value of x cubed. Now, the natural log of 1 we know is equal to 0, so our whole numerator then equals to 0, and our denominator equals to that. And you'll notice now that we're doing the limits as x approaches 0, because this function is only in terms of x now. We've made y equal to 0. Okay, so evaluating that limit, that simplifies to 0. It's always going to be 0, and therefore our limit is equal to 0. So now we need to check it along our y-axis, or our x is equal to 0 line. So in order to do it, we substitute in zeros for our x's, and then we evaluate this limit as y approaches 0, because our function is now strictly in terms of y. So our numerator then simplifies to 0, and our denominator to the absolute value of y. And it simplifies to the absolute value of y because the square root of y squared is the absolute value of y. So this limit then goes to 0. Okay, so now we check along this third line. The x is equal to y to the power of 2 over 3. And just note quickly before we go and check along this line, that you can choose anything. You could have chosen different lines to check your limit along. It didn't have to be the x-axis, y-axis, and this line over here. It could have been any lines that you thought of that you thought were the easiest to check it along and that you were able to check it along. So these were the lines that I thought were easiest, so I'm going to check it along those lines. And there's no hard and fast rule saying you have to check it along 3 lines or 2 lines or any certain number of lines. It's just so that you get an idea. And as a general guide, I would suggest you check it along 3 lines. Okay, so checking it along this third line, which is x is equal to y to the power of 2 over 3. We substitute now y to the power of 2 over 3 for all our x's in this function. Okay, now since this function is strictly in terms of y, our limit is of y tending to 0. Okay, so this y to the power of 2 over 3, we can take the exponent out of the absolute value, and we have 3 times by 2 over 3. And 3 times by 2 over 3, our 3's cancel, and we're just left with the absolute value of y squared. Now, the absolute value of y squared is equal to y squared, and it's equal to y squared because both of them are going to be positive. So I hope that makes sense to you. So then what we can do in this denominator over here is we take the square root of 2y squared. And the square root of 2y squared is the square root of 2 times by the square root of y squared. The square root of y squared, as we said earlier, is the absolute value of y. Okay, so now we have a function that is a lot simpler than we originally started with, and we do still have a problem though. We have our absolute values here, and it's difficult to evaluate limits of absolute values because they can be different from the left and from the right, because our function from the left is going to be negative, and our function from the right is going to be positive within our absolute value. Okay, so what we then need to do is we need to split it up. So as y approaches 0 from the right-hand side, here's our Cartesian plane, and we're approaching y equals to 0. And as we're approaching y is equal to 0, from the positive side, we're coming down like that to y is equal to 0. And if we're doing that, then our y is strictly greater than 0. And if our y is strictly greater than 0, then absolute value of y and y are going to be the same thing. So we get rid of the absolute value, and we're left with this function over here. And we got this y to the power of 1 over 3 in the denominator, because we had y to the power of 3 over 3, or y to the power of 1 in the denominator, and y to the power of 2 over 3 in the numerator. And those simplify to y to the power of 1 over 3 in the denominator. Okay, so we're left with that function when y is greater than 0. And as we approach 0 from the left-hand side, or the negative side, then what we are saying, if we look at our Cartesian plane then, is we're approaching 0 like that. We're approaching it from this negative space, which means our y is going to be strictly less than 0. And if y is strictly less than 0, but it must still be the absolute value, then we must multiply that negative number by a negative, because by doing so, we make it positive. So now, every time we see an absolute value of y, we replace it with negative y. Okay, and that leaves us with those two limits over there. So now what we're going to do is we're going to use L'Hopital's rule to simplify these limits to try and evaluate them. So we take the derivative of the numerator divided by the derivative of the denominator, and we do the same for both of those limits. And then we simplify them, and we're left with those limits. And if we substitute now our 0 into those two equations, we get 0 and 0. And that's very nice, because we know then that the limit as y approaches 0 from the right and from the left are both 0, which means the limit as y tends to 0 is 0. Okay, so we've successfully checked our limit along these three paths, and we've got the same answer in all cases, which is 0, 0, and 0. So we can't safely conclude that our limit equals 0, and we can't safely conclude that it exists. However, we can't conclude immediately that it does not exist. So what we can do then is we can consider L equal to 0 as our candidate. So what that means is we're going to try and prove our limit to be 0 of f of x of y, as both x and y tend to 0. Okay, so if we take the absolute value of our f of x and y, then that function is going to be strictly greater than or equal to 0. It's not strictly greater than or equal to 0. It's greater than or equal to 0, sorry. Okay, so the absolute value of f of x of y is going to be this function over here. And the reason why that works is because our denominator, if you look at our original function, is this, which is always positive. So we don't need to take the absolute value of the denominator. And if you look at our numerator, taking the absolute value of it, we have those two terms. So we need to take the absolute value of x, because x could be negative, x could be positive. We don't know what it's going to be. And the natural log of 1 plus the absolute value of y, well, if we look at a graph of the natural log, it looks something like that. And that point over there is where x is equal to 1. And beyond x is equal to 1, our natural log is strictly positive. Okay, and if our natural log is strictly positive, greater than 1, when we're adding a positive value to 1, which means greater than 1, then our natural log is always going to be positive. So we don't need to take the absolute value of the natural log. We only need to take it of that x over there. And so that's how we arrived at that function. Okay, now something to note, and something that is taken as a given, and something that you can prove, is that the natural log of 1 plus the absolute value of y is less than or equal to the absolute value of y. And that works generally for replaceable functions of the absolute value of y. So, for example, the natural log of 1 plus t will be less than or equal to t. And if we were to graph that, it would look something like that, and you can see that our t is then greater than our natural log. So that's a general idea behind that statement. And that statement is crucial because if that's going to be less than or equal to that, then we can reduce that to this function and say that this function is greater than this function. And that's so because this part of the numerator is less than that part of the numerator, and everything else remain the same. Okay, so we then have that this function is greater than or equal to 0. All right, but now we have to try and reduce this some more so that we can evaluate it, so we can perform the squeeze theorem. And if we do that, then we'll notice something. We'll notice that the absolute value of y over the square root of this positive number plus y squared is going to be between 0 and 1. And the reason this is true is because the absolute value of y is equal to the square root of y squared. And in the denominator, we have y squared plus some positive number. And so you can therefore see that the square root of y squared plus a positive number is going to be greater than the square root of y squared. And so that then must lie below 1. It must be less than 1. But since both of those are positive, it must also be greater than 0. So we get then that it lies between 0 and 1. Okay, so that's very helpful. And that's very helpful because then we know that that function as a whole is less than that function. And that's so because if we multiply x by a fraction, then we get a smaller function. All right. So that simplified life dramatically for us, because now if we evaluate the limit as x and y tend to 0 of this function of x, we know that that's going to be equal to 0. And that's very, very convenient, because now we've squeezed the function of x and y between 0 and 0, because this tends to 0. Okay, so then by the squeeze theorem, we can conclude that the limit as both x and y tend to 0 of our function of x and y is equal to 0. I hope you found this video useful and interesting, and if you did, please don't forget to leave it a like and subscribe to my channel. And if you have any questions regarding the content I've covered today, this is a very rigorous limit and proof. Feel free to leave a question in the comment section below. I'll be happy to tend to your concerns or worries regarding this. Thank you for watching.